where are we going with this nitrogenase stuff? I've talked about low-level things like ammonia. I've talked about amino acids. What are these details just are not getting to the core point? So let's take a broad spectrum view of how all this stuff works. Quantum computers, physics, inorganic chemistry, organic chemistry, biochemistry, biology, and did I start with quantum computers? Because that's the whole reason I got started with this thing. This problem needs a quantum computer to get it figured out. Do you want to look at this and try to bring all this stuff together? Let me show you an illustration of what I just talked about. Okay, here we are. Quantum computing. What do we need this for? Simulation mapping. Basically, another way to think of it is this nitrogenase is a quantum computing operation in itself. So quantum computing is made up of atoms or whatever quantum type devices, so it can actually act like the nitrogenase, and we can figure out ways to do nitrogenase without this super complicated molecule. We can design one that does the same kind of interactions that makes it act as a catalyst that produces all this energy to break the triple bond of nitrogen. Inorganic chemistry involves this complicated molecule that we're trying to simulate or design a new one that's not so complicated but does the same thing. We have organic chemistry. Well, anything with carbon is going to involve a study within the organic chemistry realm. And then biochemistry. Well, what's actually doing the nitrogenase process? Well, it's bacteria for the most part. And these bacteria, that's biochemistry that's going on inside there. And biology, finally we get to the fact that we have actual creatures that are aiding in this nitrogenase process. And then up here, whoa, quantum tunneling, spin, energy flow. That's pretty deep. Didn't even realize this thing was in there. So what we're going to try to do in this video is I'm going to try to break each one of these down into separate categories and see if we can expand on this a little bit. At the center of that diagram that we looked at, there was just nitrogenase in the middle. So that's the goal. Here's to state the problem. A quantum enzyme beyond classical reach. And here's a little bit more information about it to help understand that. This giant molecule has greater than 300 active electrons. And we have to keep track of all the correlated motions to figure out how it operates chemically. A classical computer just can't handle all this stuff. So what we do is we actually model the 300 active electrons with quantum devices themselves, which act like electrons. Let's focus on the quantum computing aspect specifically. Hilbert spaces, superposition, and entanglement. That's exactly what happens inside the catalytic process. Here's the relevant algorithms, and each one of these is probably a video in itself. This chart looks at it a little bit differently. What's the electron tunneling and spin coupling? Well, that's what happens during the chemical process. And a quantum computer can simulate all of these things if you have enough qubits and you have the qubits that are coherent, which we don't have that yet, but we want to prepare for it and plan all the different aspects of our experiments. We already talked about the metal cluster orbitals, hydrogen transfer steps. explore reaction pathways via potential energy surface reconstruction. So this is how the quantum computer does help out with the organic chemistry part. Then if we talk about the biochemistry part, this couples electronic state transitions to it gets complicated. Like I say, each one of these is worth a video. The biology is a little bit different than what I expected. It's actually environmental adaptation methods. So we try to use those same techniques when we perform quantum computing algorithms. This gets back, this topic here where it says philosophical, this gets back to what I said about nitrogenase is actually a quantum computing operation on itself. If you look at each one of these quantum actions that takes place. Manipulates electron and proton spins through coherent tunneling, orchestrates discrete quantum transitions to achieve macroscopic function. Its efficiency hints that biology has evolved quantum optimization long before human engineers conceived it. So we're thinking all we're doing is copying what biology has already done with the quantum computer system.